momentum conservation. We'll start by figuring out when momentum is conserved. Then we'll analyze a couple of physics problems. One simple problem just using momentum conservation, and another more complicated problem using momentum conservation and energy conservation in tandem. If you recall, we derived that the net force equals a change in momentum with respect to time. dp dt equals net force, with momentum being defined as the mass times the velocity. If the net force is zero, then the change in momentum with respect to time is also zero. That means that momentum is conserved. The initial momentum equals the final momentum. Also, momentum is a vector quantity. That means that we can write the components of the conservation of momentum. Each of these components is separately conserved, can be separately conserved if the net force is equal in those components. Let's start by solving and analyzing a simple problem where a car with mass m1 moves on a frictionless surface with velocity v1 in the positive x direction toward a car with mass m2 that is at rest. The two cars collide and stick together. We want to find the final velocity of the two cars. Start by thinking about assumptions and drawing a diagram. We'll assume these cars are particles and that our level ground only contains one component of momentum. We diagram a time 1 when the car 1 is moving with velocity 1, 0, car 2 is at rest. Then the final time we have the cars stuck together, so m1 plus m2 is the final mass. We're asking for v final. Now let's define our known and unknown variables. We know the masses of the two cars, m1 and m2, and the initial velocity of car 1, v1, 0. We want the final velocity of the cars that are stuck together. We can just call that v final. Start with our general equation. Initial momentum in the x component equals the final momentum in the x component. We write the initial momentum for the whole system, m1 v1 0 plus m2 v2 0 equals the final momentum, m1 v1 final plus m2 v2 final. Now we'll specify this general equation for our system. m2 v2 0 goes to 0 because car 2 is at rest initially, so we have m1 v1 0 equals m1 plus m2 v final. We've combined the two masses because they stuck together, and we can just call the final velocity v final instead of designating it as v1 final and v2 final. Now we just divide through both sides by the sum of the masses to get our answer, m1 over the net m1 plus m2 times v1 0 equals v final. We can divide our equation through by m1 to make it a little bit more easy to analyze. In this case, what we can see is the final velocity is larger if our initial velocity is larger. That makes sense. If the car 1 is moving faster before they collide, the two cars together will be moving faster. And putting the masses into a ratio like this makes the masses easier to analyze. We can see that if m2 is larger, the final velocity is actually smaller. If m1 is larger, the final velocity is larger. This makes sense as well. A larger mass car running into a smaller mass car will end up at a final higher speed. All right, let's do another more complicated problem. Here we have a block of mass m1 sliding a distance d1 down a frictionless stationary ramp of angle theta. It strikes and sticks to a block of mass m2 at the bottom of the ramp. The two blocks then slide along the horizontal floor with a coefficient of friction mu k acts between each block and the floor. How far do the blocks travel before stopping? We'll use our same system of solving and analyzing our problem, starting with a diagram and assumptions. I've drawn out the diagram here. It's got D1 along the ramp. We're trying to solve for D2. Our assumptions are that we can treat our blocks as particles. We don't have any air resistance in our system. Our known variables are the two masses m1 and m2. The distance m1 slides along the ramp d1, the angle of the ramp theta, and mu k, the coefficient of friction between the two masses and the floor when they slide along the distance d2. The distance d2 is what we're solving for. We want to develop a strategy for solving this problem. We can't do the whole problem as conservation of energy, because there's some unknown amount of energy involved in sticking the two masses together. What I can do is use conservation of energy to find out the final velocity of m1 when it reaches the bottom of the ramp. Then I can use conservation of momentum when the two masses stick together, giving me the velocity when they start to slide. And then I can use energy approach to find out how far they've slid. So I start with conservation of energy. U0 plus K0 equals U final plus K final. My initial potential energy is m1 g d1 sine theta. d1 sine theta is the height. And my kinetic energy to begin with is 0. I'll let my potential energy go to 0 at the bottom of the ramp, and my final kinetic energy of mass m1 would be 1/2 m1 v1 squared. I'll let that velocity be v1. I can solve this equation for v1. v1 equals root 2g d1 sine theta. Now I'll do a conservation of momentum approach for the time when the blocks are sticking together. P0 equals P final. The initial momentum is m1 v1. The final momentum would be m1 plus m2 quantity multiplying onto v2. I'll let that v2 be the initial velocity of the blocks as they're starting to slide. Now I solve this expression for v2. I've substituted in my expression for v1, root 2g d1 sine theta, and divided through by m1 plus m2 to get the final value for v2. Now I can do a work kinetic energy theorem approach for the blocks sliding along. I have the change in their kinetic energy equals the work done by friction. The change in their kinetic energy, since their final kinetic energy is 0, their final velocity is 0, is minus 1/2 m1 plus m2 on v2 quantity squared. That's their initial velocity, equals the work done by friction, which is mu k times the normal force, which is m1 plus m2 multiplied by g, and the distance d2. Notice the two minus signs are going to cancel here. The work has a negative sign because the force is in the opposite direction of the displacement. For the next step, I've canceled the term of m1 plus m2 on both sides and the minus sign. I've substituted in v2 squared. That gives me an m1 over m1 plus m2 quantity squared. And then take the square root term, 2g d1 sine theta, and the 2 cancels with a factor of 1/2. That just equals mu k g d2. My terms of g are going to cancel on both sides, and solving for d2, I just divide through by mu k. I can again do the trick of dividing through by m1 to get a factor that's just a ratio of m2 and m1. That makes it easier to analyze. What I can see is that d2 will be bigger for the larger d1 sine theta. That makes sense. If the block started from a larger height, or a larger d1 sine theta, then you'd expect the two blocks to travel farther as they moved along after sticking together. d2 is smaller for larger mu k, which makes sense. Larger coefficient of friction will make the distance that they travel along less. And also I can see that if m2 is larger, then they will travel a smaller distance, and if m1 is larger, they'll travel a larger distance. That also makes sense, because m1 is carrying the energy coming down off of the ramp. So to recap, what we did was we talked about when momentum is conserved, that's when the net external force is zero. We can use momentum conservation for inelastic collisions. Those are collisions where two things stick together completely. Energy is not conserved during a completely inelastic collision or even a partially inelastic collision. For complex problems, there may be parts where energy is conserved, but momentum is conserved in other parts, so we can use a multi-stage approach for problems that are more complicated. Thank you very much for coming, and please come again soon.